Okay, so first problem on Airy stress functions. So what we plan to do is we have this beam. This yellow thing is the beam. It is our V, and the red line is delta V. We have a distributed load on the top, and then uh, the depth of the beam is 2b, the length is 2a, and the thickness, out of plane thickness, as shown here, is, let's say, 1. Okay. Now, at the ends, you have a reaction force P naught A and P naught A at the two ends, two edges, and you are supposed to find the stress distribution in the yellow region for this. Now, we have a simplified Moss solution to this problem. And it goes like this. So this is a simply supported beam with a distributed load of P naught. So what you do is you draw the shear force and bending moment diagram of this. To do that, you figure out that the reaction forces here are P naught A and P naught A. Okay. So depending on your convention, I use the convention that upward is positive. So using that convention, so you draw the shear force diagram. So you have P naught A here, you jump P naught A. Then this is a negative, constant negative load. So that means the slope is negative, linear in the shear force diagram. So you come down, and then again when you reach the end, you have a jump of P naught A. So this is your shear force diagram, and if you look at the variation of the shear force, you can write it Vx1 as minus P naught x1. Okay, so this line can be written as minus P naught x1. If you want to calculate the bending moment diagram from here, you would realize that the bending moment diagram would be parabolic. It would be 0 at this end, and at this end it would be maximum at the center. And then if you use your conventions and your techniques for drawing the bending moment diagram, you would see that it would have a slope which is increasing in the negative direction. So quadratic function with increasing negative slope will give you this. This part would be simply symmetric, and this is your bending moment diagram. The maximum value of the bending moment would be half P naught A square, which is the area of this triangle. And then if you write it, as a function, this is the function that you get. I have messed it up. This is the function that you get. This is the function describing this curve. Now what we know about the bending moment, the stresses in an Euler-Bernoulli beam is that sigma 1 is the only non-zero component of stress. Everything else is 0. So 1 is this direction. This is x1. So, and with sigma 1 varies linearly through the thickness, through the depth of the beam. So sigma 1 is minus my by I. That is the equation that you had learned. So in this case, y is x2. So it is m, which is a function of x1 times x2 divided by I. I is 1/12 bh cube. In this case, the width of the beam is 1. The height is 2b. So that gives you 2/3 b cube, and that is your I. If you plug it in here, mx1 is this, mx1 is this. If you plug it in, this is your sigma 1. This is your sigma 1 that you get from the simple Euler-Bernoulli beam theory, assuming that, which assumes that sigma 1 is a linear function of the distance from the neutral axis. okay, linear function of the y distance from the neutral axis, and is also proportional to the moment at the cross section that you are considering. So considering that this is your stress, and then putting the expression for moment for a distributed load, this is the final expression for the stresses. Now, uh, Euler-Bernoulli beam theory does say that sigma 1 is the only non-zero stress and every other stress component is zero. But we do a shear correction. We do a shear correction to the Euler-Bernoulli beam theory, and you have learned about this in MOS towards the end of the MOS course. That as an afterthought, we do a shear correction for various reasons that I will explain sometime later in the course. And this shear correction is given by this expression, VQ by I. I we have already found out is 2/3 BQ. V we have already found out from here. V is the shear force. So Vx1 is minus P naught x1. So we have figured out that this is minus P naught x1, and q is something that we need to find. If you would remember your MOS, you would remember that q is q at a distance x2 from the neutral axis is the moment of this red area, which means that q is uh, the area itself multiplied by the distance of its centroid, which comes to, if you work it out, b square minus x square by 2. You plug it into this expression here, and this is the expression for sigma 1 2 that you get as a result. So sigma 1 2, the highest power is x2 square x1, that is it's a cubic equation. And then here also you see x1 square x2, that it also is a cubic equation. So sigma 1 1 and sigma 1 2 are both cubic equations, sigma 1 1 coming from the Euler-Bernoulli beam theory, sigma 1 2 coming from the shear correction. Now let us go ahead and look at this problem a bit carefully and figure out if we want to solve it not as a beam theory problem but as an extended continuum, which is the yellow region on which we need to find out all the stresses. What would the boundary conditions be? So what would be del Vt? What would be del Vu? What you see here is on all boundaries of this particular geometry, nowhere is displacement specified. So this del Vu is a null set. Del Vt is the entire boundary del V. Now, on different parts of this boundary, the boundary conditions are different. For example, on the lower edge, which is, let me rub this. On the lower edge, the normal has components of 0, minus 1. That's the normal components. So T1 bar is sigma 1 1 n1 plus sigma 1 2 n2. And T2 bar is sigma 2 1 n1 plus sigma 2 2 n2. However, this is a traction free surface, so T1 bar is equal to 0, T2 bar is equal to 0, N1 is 0, so this is 0, this is 0, this is minus 1, this is minus 1, which means that sigma 1 2 equal to sigma 2 2 equal to 0 on this boundary. On this boundary, sigma 1 2, sigma 2 2 equal to 0. What about the top boundary? On this boundary, the normal is 0, 1, which means that T1 bar is equal to sigma 1 1 n1 plus sigma 1 2 n2. This is 0 because n1 is 0, and this is equal to sigma 1 2. So but there is no x traction on this. So T1 bar is equal to 0, which implies that sigma 1, 2 equal to 0 on the top surface. T2 bar is equal to sigma 1, 2 N1 plus sigma 2, 2 N2. So this is equal to 0 because N1 is 0, but this is equal to sigma 2, 2. And there is a 2 traction which is equal to minus P naught. So minus P naught is equal to sigma 2, 2 on the top surface. So on the bottom surface, we have sigma 1, 2 equal to sigma 2, 2 equal to 0. And on the top surface, we have sigma 1, 2 equal to 0, sigma 2, 2 equal to minus P naught. So these two surfaces are quite unambiguous. What about this? On this, we have the normal to be, let's take this, which is the same. So the normal is 1, 0. Okay. However, what is the traction T bar? The T bar traction the T-bar traction is not actually clear from the problem. So this might be a distributed force over this whole edge, or this might be a concentrated force at the corner, as would happen if it was subjected to a boundary condition like this. But what we can say is that the total force in the y direction is equal to P naught A. We can also say that the total force in the x direction is equal to 0, and if we want to give more information, we can even say that the total moment of these forces also has to be 0 because there's no moment applied at the free edges. So the total moment is 0, total force in the x direction is 0, and total force in the y direction is equal to P naught A. These are conditions that would apply at x1 equal to a as well as at x1 equal to minus a. But we are going to write this for x1 equal to a only because the ones at minus a would be identical. Okay. Now, how do we write this in terms of the stresses? So if you look at the traction, so traction has two components. So traction at any point here would be like this, in some vector like this. So it will have two components, T1 bar and T2 bar. The normal is in the 1, 0 direction. So T1 bar would be sigma 1, 1 N1 plus sigma 1, 2 N2. This is 0 because N2 is 0. This is 1. So T1 bar would be equal to sigma 1, 1. T2 bar would be equal to sigma 2, 1 N1 plus sigma 2, 2 N2. This is 0. So sigma 2 bar would be equal to sigma 1, 2. Okay. Now, now try to find the total force on this edge. The total force on this edge would be, say in the x direction, would be T1 bar multiplied by a small element of area dx2 into 1, remember the depth is 1, integrated from minus b to b. So this would be your F1 in the one direction. So this would be the total force in the one direction, and we know that T1 is equal to sigma 1, 1 for that edge. For that edge, T1 is sigma 1, 1. So F1 is sigma 1, 1 dx2. Similarly, F2 is equal to minus b to b dx2, and this is equal to sigma 1, 2. So force F1 is sigma 1 dx2 minus b to b. F2 is sigma 1, 2 dx2 minus b to b. We do not exactly know what the variations of sigma 1, 1 and sigma 2, 2 on the edge are, but we know that this is equal to 0 because there's no external force in the x direction. this is equal to P naught A. Okay, this is equal to P naught A, and we can also say that the moment of this force is uh, this T1 bar dx1 is the x force, and then times x2 gives the moment about the center, the neutral axis, integrated from minus b to b gives the total moment on that edge m, and that is also equal to 0 because there's no external moment. So we can use these three as weak boundary conditions on the two edges, two vertical edges. We can use them as weak boundary conditions because we are having to use them because they are the distribution of tractions at the boundaries are not exactly known, and that's why we have to resort to using weak boundary conditions on the vertical edges, whereas on the horizontal edges we use exact boundary conditions. Okay, now we have to guess phi, uh, having decided the boundary conditions. So these are the boundary conditions. These are the strong boundary conditions on the upper and lower faces, and these are the weak boundary conditions at x1 equal to a, x1 equal to minus a would be similar. Okay, uh, right. Now we need to use a series solution to this problem. That's what we will try. Now, think of the situation where you are trying to guess the series based on the Euler-Bernoulli beam theory. So this is how you will go about. So you will say that, well, Euler-Bernoulli beam theory says that P naught can be a function of x1 to the power n. So P naught is the distributed load. It can be a function of x1. If it is, then dv dx1 equal to P naught is one equilibrium equation that I get from the Euler-Bernoulli beam theory, will tell me that V is x1 to the power n plus 1. Then we have dm dx1 equal to V, which means m will be x1 to the power n plus 2, right? And then the stress is m x2 by I. So the stress would be x1 to the power n plus 2 into x2. Stress will be of this form, and the stress will be only sigma 1 1. That's the only one that is allowed. So if this is the case, then remember phi is del square phi del x2 square, which means that phi will, at least in order to satisfy the Euler-Bernoulli beam equations, it has to be x1 to the power n plus 2 x2 cube, right? So this has to be the order of phi, which means that if I now have a case where P naught is a constant, so n is equal to 0, then phi has to be at least x1 square x2 cube. That means it has to be a fifth order polynomial. So fifth order polynomial is the only one that will at least satisfy the Euler-Bernoulli beam theory. Out of that, in a fifth order polynomial, the linear terms that are say linear on x1 and x2, they don't matter because the stresses are dependent on the second derivative. So these terms which are linear in x1 or linear in x2 would actually disappear when you take the derivatives. So will the constant term. So leaving the constant and linear order terms out, a fifth order polynomial will be like this. It will have 18 terms like this. You can check it out. Fifth order polynomial. So fifth order polynomial will have this form. So these 18 constants are unknown constants which you need to determine from the boundary conditions. And uh, of the boundary conditions, we may have more number of boundary conditions than there are constants. So it is going to be overdetermined or underdetermined problem, but you have to make sure that all the boundary conditions are satisfied. Remember, we have two sets of boundary conditions on the vertical edges, which are weak boundary conditions. So they have to be satisfied in a weak sense. They will not be satisfied from point to point manner, but they have to be satisfied in order for me to get to claim that I have got a solution to this problem. Another thing that needs to be satisfied is del 4 phi equal to 0. There are no body forces in this problem. So del 4 phi equal to 0 is the governing equation, biharmonic equation for area stress function that needs to be satisfied. So once I have made this initial choice based on my expectation that I at least want to fulfill the Euler-Bernoulli beam theory equations, I want to get those equations. What I do is I substitute phi into the biharmonic equations. When I do that, this is what I will get. This is what I will get, and I have worked it out. There may be errors. Please let me know if there are errors. Please work it out. So once you do that, you will the right hand side is 0. So we will say the coefficients of x1 are 0, coefficients of x2 are 0, and the constants are 0 as well. Therefore, you get these three equations. You have to get 18, remember. So you got these three equations from the fact that del 4 phi is equal to 0. That gave you these three equations in these sets of coefficients. Many of the coefficients, of course, do not appear here. Now, I have this. Now I will use the boundary conditions one by one. Okay. So first, let me substitute this form. Let me substitute this form in order to apply the boundary conditions. This is my chosen form. Let me substitute this form into sigma 1 equal to del square phi del x1 square, del sigma 2 equal to del square phi, this is sigma 2 x2 square, del square phi del x1 square, and sigma 1 is minus del square phi del x1 del x2. I will substitute this phi into these equations, and I determine sigma 1, sigma 1, and sigma 2. Again, I have done this myself, and please let me know if there are errors in these coefficients. Okay. So now, once you have done this, now let us apply the boundary conditions. What do we know? We know that on x2 equal to b, that is the top face, I have sigma 2 equal to p naught a, or minus p naught a, minus p naught, I think, minus p naught, and sigma 1 equal to 0. So I have sigma 1 and sigma 2 at x2 equal to b, and I set them equal to 0 and minus p naught, and then so here in sigma 1 I need all the coefficients to be 0. So C14 to be 0, this to be 0, this whole thing to be 0, and this whole thing to be 0. So that's what I have done. And in sigma 2 I want the constant term, that is this one, to be equal to minus p naught, and all others, this one to be 0, this one to be 0, this one to be 0, and that leads me to these sets of equations. So 1, 2, 3, 4, 5, 6, 7, 8. 8 equations. I had 3 earlier. 8 plus 3, 11. Okay. Now I do this for x2 equal to minus b. Remember, at x2 equal to minus b, sigma 2 equal to sigma 1 equal to 0. So when I put minus b to these equations, when I put x2 equal to minus b to these equations, I will get equation in terms of x1, and I equate the coefficients of that to 0, and this is again what I'll get. Please check them out. Please check them out. So these are another set of equations that I will get from x2 equal to minus p. Now, now I am still left with um, the left hand side and the right hand side, and I will use only one of them, the right hand side, let's say, because it's symmetric. I will use the right hand side, and on x1 equal to a, the tractions, remember, at x1 equal to a, the normal is 1 0. The traction t1 bar is equal to sigma 1 1, and t2 bar is sigma 1 2. So I have to calculate, I have to take sigma 1 1 at x1 equal to a, sigma 1 2 at x1 equal to a, and these are the two equations, and then I insert it into the three conditions. So this is for f1 equal to 0, this is for f2 equal to p naught a, this is for m equal to 0. I get these three additional equations, and then the task is to solve it. You can use Maple or Mathematica to solve it. Doing it by hand is very tedious. If you solve it now, then this is the phi that you will get for solve for C1 to C18. This is the phi that you will get, and this phi will lead to a stress field. So you just have to take it. Once you've got the phi, you've got almost everything. You've satisfied all the boundary conditions to get the phi, to get the coefficients of phi, and once you've got it, you've got everything. This should be p naught, I'm sorry. So once you've got this phi, you can take the derivatives. So this is del square phi del x2 square. This is minus del square phi del x1 x2, and this is del square phi del x1 square. And as you can see that sigma 1 1 is there, sigma 1 2 is there, and sigma 2 2 is also there. So in your MOS course, this was equal to 0 always. This was always equal to 0, but what you see here is that sigma 2 2 is present in this particular solution. Sigma 2 2 is indeed present in this particular solution, which is a more exact one compared to your Euler-Bernoulli beam theory. However, the Euler-Bernoulli beam theory is a remarkable approximation. When the Euler-Bernoulli beam theory was derived, theory of elasticity was not developed. So Euler and Bernoulli derived these equations completely based on intuition, and the intuition is remarkably accurate. Let me try to impose that on you. Look at the sigma 1 2 equation. Look at the sigma 1 2 equation, right? And this is exactly same as the sigma 1 2 that we got from the shear correction. So this was the shear correction that we did based on this strength of materials formula, that sigma 1 2 is shear force into Q by I. So based on that formula, the shear correction that we did is exactly the same as the shear stress that we get from this extended procedure. Sigma 1 1 is not exactly the same, but if you scale the terms, you will see that out of the four terms here, in sigma 1 1, two terms were already there in the Euler-Bernoulli beam theory. So I think 15 x1 square x2 and 15 a square x2, these were terms that were already there in the Euler-Bernoulli beam theory. I am just scaling this to 15 and this to 20. I'm just multiplying by something to scale this up. The Euler-Bernoulli beam theory equation that we had obtained earlier. I'll go back to that. Yeah, this is the this is the Euler-Bernoulli beam theory equation. I am multiplying both sides by numerator and denominator by 5, and then making it look similar to the elasticity solutions that we have just found. So if you look at them, you will see that the two terms in the Euler-Bernoulli beam theory do exist in the elasticity solutions also, and uh, the other two terms, the ones that, so this one exists, this one exists, this one will be, and this one are both dependent on x2. So if you have a very thin beam, if you have a beam which is not very deep, it's thin, in that case x2 is a small number, so this is going to be a very small correction to the Euler-Bernoulli beam theory, and this is going to be also a small correction to the Euler-Bernoulli beam theory. So the two dominant terms for a thin beam are present in the Euler-Bernoulli beam theory. What is not present is actually a small correction in case of thin beams. However, for deep beams, for beams which are deep, this solution will work, while Euler-Bernoulli will not work because of this term, which increases as the cubic root of the depth. Okay, so the Euler-Bernoulli beam theory works for a thin beam very well, and it does not work for a deep beam that well. Of course, sigma 2,2 is not there. Sigma 2,2 has to be there, and for deep beams, again you will see that sigma 2,2, these terms are dependent on x2. So this x2 is supposed to be small for a thin beam. So sigma 2,2 will be pretty much negligible for a thin beam. For a thick beam, however, for a deep beam, the Euler-Bernoulli beam theory will not work very well, and the elasticity solutions will give you a much better solution. For a thin beam, however, for which Euler and Bernoulli intuitively derive the solution, their intuition turns out to be extremely enduring and extremely accurate. Okay. The one more point that I want to make is about these weak boundary conditions. So now that we have got the solution to sigma 1, 1, so we have got this solution, we can now put x1 equal to a and write down sigma 1, 1. If we do that, this is what we will get. Sigma 1, 1 at x1 equal to a is this. I've just put a in the equation, and you will see that this is identically equal to 0 only at x2 equal to 0, that is at the neutral axis. In other places, though the integral of sigma 1, 2 is equal to 0, it is not exactly equal to 0 on the edge. Okay. If you look at sigma 1, 2 at x equal to a, if you look at this one and the moment due to this one, moment due to sigma 1, 1, you will see that the moment integrated from the lower edge to the upper edge is equal to 0. And sigma 1, 2 integrated from the lower edge to the upper edge, that is from minus b to b, will give you p naught a. Okay. But the boundary conditions are not satisfied point to point because we have not used exact boundary condition. We have used a weak form of the boundary condition on the left and right edges. Now, what is the significance of this? What is the price for this? Okay, the price is the following. So here is the solution that is derived, that we just derived. And to plot this in MATLAB, I have used P naught as 1 kilonewton per meter and A by B equal to 10, which means this is a thin beam. Its length is much more than its depth. So this is the variation of sigma 1, 1. Each color represents a range of values. Okay, and I think yellow is maximum positive and blue is maximum negative. So you can see that it's pretty much symmetric about the neutral axis, and it's pretty much straight, varying with x2 except towards the edges, And This is an experiment that you will see in your photoelasticity courses if you have not seen it already, except at the edges, it is pretty much like what you expect from the Euler-Bernoulli beam theory, right? Uh, Now here is an exact finite element solution. This is an exact solution with roller supports here. Okay. Roller supports mean that these 2 points are part of your del VU where U2 is equal to 0. U2 bar is equal to 0. So at these two points, the rest of it, this part and this part, attraction free, which means that sigma 1 1, so the normal again is 1 0 here. So sigma 1 1, so T1 bar is equal to sigma 1 1 is equal to 0. T2 bar is sigma 1 2 equal to 0. So on this edge, sigma 1 1, sigma 1 2 both have to be equal to 0. Similarly, on this edge, sigma 1 1, sigma 1 2 have to be 0, which will satisfy the conditions that we had, that the total normal total integrated force in the x direction has to be 0. So integration of sigma 1 1 will of course be 0. The moment will be 0. Sigma 1 1's moment about the neutral axis will of course be 0 because sigma 1 1 is 0. And the total force in this direction coming from sigma 1 2 will be 0, but there would be a concentrated force here equal to P naught A. That will give you the total force to be equal to P naught A. Now, this will of course satisfy the weak boundary conditions, but the strong boundary conditions, which are sigma 1 1 equal to sigma 1 2 equal to 0 on this edge for this particular problem, will not be satisfied by the solution that we have just found. Now, we can of course solve this problem exactly in finite elements using finite elements. And now if you look at the solution, you see something which is quite remarkable. You see that here close to the boundary, the stress distribution is different from what you have here. Close to the boundary, the stress distribution is different, but away from the boundary in this region, let's say, the stress distribution seems to be affected very little by the different boundary conditions that you have. The weak boundary conditions are different in this case and in this case. In spite of that, the solution away from the boundary does not seem to care. So this is known as the Saint-Venant's principle, which says that the effect of boundary conditions are local in nature. They die down very quickly. The effect dies down very quickly as you go into the interior of the body. We are not going to spend more time on the Saint-Venant's principle, but the effect of boundary conditions represented by the weak boundary conditions that we have used dies down very quickly as you move away from the edge, and far away from the boundaries, the solutions do not really care about the exact nature of the boundary condition. How far away from the boundary will the conditions die down is depends on the problem, but they do die down very quickly as you move away from the boundary. So the equilibrium equations, the free body diagram for this case, as well as for the case that we have solved with Airy stress function, are the same. The integrated boundary, integrated forces and moments are all the same, but the point-to-point strong boundary conditions are different. In spite of that, the solution inside the material, inside the body, is almost completely identical. Okay. This is the Saint-Venant's principle, which we make good use of in engineering. The fact that effect of boundary conditions are local to the boundary and die down quickly as you go to the interior of the body. This is a principle that is tacitly and non-tacitly used very often in solving engineering problems. The other thing that I was saying uh, is about the depth of the beam. This is sigma 1 1. This is sigma 1 1 for contours of sigma 1 1 for our Euler-Bernoulli for our elasticity solution. This is the functions that we have obtained for sigma 1 1 1 2 and 2 2. This is the function for sigma 1 1 that I have plotted for a beam with a by b equal to 2. So this is a deep beam. This is a deep beam. And now you see that the solutions here are very different. Solutions here are very different. And this is the Euler-Bernoulli approximation for sigma 1 1, and this is the Airy stress function elasticity. So elasticity solutions for deep beams, if you looked at sigma 2 2 and sigma 1 2, you would see even more, they're even more unlike each other. Sigma 1 1 is still looks the same, though at the boundaries you now have a completely different distribution which persists for some time. So Euler-Bernoulli is not a good idea for deep beams, but for shallow beams Euler-Bernoulli works very well. And that is a fact that we have just proved by solving this problem of a distributed load on a beam using exact elasticity solutions. So I'll end this by saying my favorite quote, that engineering is the art of making intelligent approximations. And probably in the history of engineering, there is no better and no more enduring approximation made than the Euler-Bernoulli beam theory.